Okay, we solved the heated rod problem, at least as posed here, where the temperature is held at 0 at each end of the heated rod. We got a partial differential equation boundary value problem, and we solved that in a previous recording. Not going to go through all that again here. But we got to the point where, well, we used the superposition principle. Let's see. We got a solution that satisfied everything except the initial temperature in the rod. Got an infinite number of solutions. The superposition principle said the linear combination of those solutions is also a solution. So we got this as a general solution. Didn't know what the a sub n's were until we used the initial condition, which said this, because at time t equals 0, this all becomes 1, and we had this situation here. For this general f of x, if we don't know what f of x is going into it, we had to expand this f of x using a sine series. Now I'll get into what I call the simple method, where this initial condition already looks like what these guys do. Now, this is an infinite linear combination of sine of n pi over Lx. When we did it for a general function f of x, we expanded that f of x using the sine series so that the a sub n's, we just needed to match coefficients. Now let's look at what I call a simple case, where that initial function, that initial temperature across the rod is this thing, where these are both in the same format as our general solution. Sine of some integer number of pi x over L. When that's the case, you don't have to solve, you don't have to take an integral. Look what we had. We had this guy, our general solution at time equals 0, equals our initial, which in this case is that. And look, we just want to match terms. When n equals 3, I have this. And when n equals 7, I have this. So what do I have? That means a sub n equals 2 when n equals 3. A sub n equals 5 when n equals 7. And for all other n's, a sub n equals 0. So there's my a sub n's. This was the total general solution for all time, which now I just plug in. I'm going to have an n equals 2, or excuse me, n equals 3, where my a sub n now equals 2. And then I'm going to have an n equals 7, and the a sub n there is 5. So here's my total solution that satisfies everything, all boundary conditions and the PDE itself, and I didn't have to take an integral anymore. That's called the simple case. In both cases, all I'm doing is matching coefficients. In one case, I match the coefficients a sub n to the coefficients of the Fourier sine series. In this simple case, I'm matching coefficients, these a sub n's, to things that match my initial function, which was already in a format that matched my solution. Anyway, that ends our initial foray into partial differential equation boundary value problems. And as much as we're going to deal with the heated rod problem, we'll do some other PDEs in another module and future recordings.